It's 2 hours UTC and it's time for Astronomy Daily Live. Hey, everybody. Hope everybody's doing well out there in the universe. Um, Although I'm pretty limited in terms of communication, right? I can only speak to those on this planet who are connected to this amazing um, internet. But hey, hope everybody's doing well. You can call me Cosmic, and welcome. Come on in, join the circle of friends. Let's talk astronomy for a while. I've been looking at some data I collected a couple of nights ago, and so I want to go over that a little bit and show you the trouble I'm having. so, so yeah, come on in. This is just a casual, fun get together every single day at um, same time, same virtual place. I like to see this as sort of like a virtual porch, right, where we're all um, gathering um, um, together, grabbing our comfortable lounge chairs. There's an awning, but we can sort of see the sky. The setting sun here. Here, the sun is just beginning to set. So it's gotten warm. I think we last week we got our last sort of cold spell last night. So I think southeastern Arizona, United States, is definitely into the summer season. It was definitely very easily in the 90s Fahrenheit here today, which is not entirely unusual, but yeah, it's great. It's great. I love it. I love the heat. I I love everything about this place. So, cheers. So Bobby's already in the chat. I see Tom there is in the chat. So hey, I hope everybody's doing well out there. As I as I said, this is just a casual, fun get together of friends every single day. I'm trying to find my core group so we can chat up all things astronomical for a while. You know, turn off the TV, forget about the news. Let's think about the universe for an hour-ish or so. Sometimes a little bit less, sometimes a little bit more. But yeah, let's think about stars and galaxies and binary stars and spectra and magnitudes and uh, astroseismology and exoplanets and rockets and Mars and Saturn and Uranus and Mercury and Zubin El Ganubi and Betelgeuse and Capella and Sirius and uh, uh, spectroscopy and polarimetry and telescopes, reflectors, refractors, eyepieces, finder scopes. Uh, how about taking astronomical data of some sort and turning it into art? You can sort of see behind me here, sort of blocked by the telescope. This is my artwork that I created by taking the orbits of Jupiter's four Galilean moons and uh, representing them in some way, adding some color, adding this and that, and coming up with um, interesting shapes. This this particular piece here I call an orbital crystal, and this was one of four pieces that I put into an art show last February, um, and there were um, 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 two categories of art. There was I think they called it visual art and data art, and each category had a first place, second place, third place, and an honorable mention. So one, two, three, four um, for visual art and data art, and uh, uh, some people watching on their smart TVs. Uh, you can participate in this, Bobby, any way you want. I would like active participation. So if you're able to keep up with the chat and all of that, that is awesome. That's very, very awesome. So yeah, cool, cool. Hello. Watch me any way you want. Watch me any way you want. So anyway, so yeah, this and um, four other pieces, two prints, and I created a video as well. Put that into the show. There were over 200 entries, 200 um, entries, and eight prizes, right? First, second, third, honorable mention. And this particular piece in the data art category got an honorable mention. Here it is. Hold on. It's actually right. It's right there. But I'll go grab it. Hold on. So there it is. Can you see that? There we go. There we go. Honorable mention. Yay. Yay. So yeah, pretty happy with that. All of my art is available. If you want to put it on your wall, contact me. Send me an email, cosmiclettuce@gmail.com, and I will hook you up. You can choose your size. You can you can choose your size, and I've got a bunch of different arts. So yeah, and I think I posted most of these, or well, not most of these. I posted some of my art on my Discord server. So make sure to get onto that. There's a link to it down below in the description, and you can join the uh, active community there. So how did I get it? There were judges that looked at every entry, and that one impressed them enough. So yeah, yeah, very surprising because there was some pretty good stuff there. In fact, let's see, can I think let me go over here and see if I can find the link to it, and I'll put that in the chat. Um, uh, I think this is it. Yeah. Oh, okay. So actually, the two categories was fine art and data art. So let me put this in the chat link. Copy and paste. Okay, there you go. There's that, and then I'll put it over on the Discord. I'll put it over on the Discord server too, so you can have a look there. You can see. I don't think they put. You know, they they didn't post every single one up on this site, but but for the most part, they they did. So yeah, feel free to take a look at that. There was some really cool stuff. So I am definitely honored to have. Well, okay. In terms of entry, they I think they had something like 220 entries, and they accepted like 208 of them. So they pretty much let everybody in. Um, so that uh, yeah, I mean, I guess it had to be like really terrible or not appropriate or something. I'm not exactly sure what the criteria was for non-acceptance, but yeah, pretty much everybody got in, but there were only actually, I take it back. I think there were nine uh, winners, nine winners. There was a People's Choice, and then first, second, third, fourth in both fine art and data art. And yeah, if you go to that page and go all the way down to the last one, honorable mention, there I am. There I am. So very cool. I'm going to start my live stream here on my smartphone because I like to monitor that if I can. All right, well, come on in, everybody. Now, this gathering of friends, right, is for newbies who don't know um, anything about things astronomical. Um, uh, it's for the amateur who just wants to, think about astronomy more, maybe, you know, gather, tidbits of information. Um, Most amateurs just like to be around each other. So, because there's so much to talk about, right? But this live stream is also for pros. I want some pros to start coming in here. Now, pros, you know, are usually pretty busy. This is sort of their livelihood, right? So they have to sort of be on top of things, and unfortunately, um, most um, professional astronomers spend at least half of their time looking for money, right? Writing proposals for grants, um, and all of that. And most of that money goes into um, uh, paying students, right, for work. So most professionals, at least that I've observed, um, spend very little time actually doing their own research. They usually, um, you know, are are doing research, but a lot of the grunt work, a lot of the actual, data reduction and the analysis, and you know, making plots for papers and all of that um, is is done by students. I was in the data art. So all the way at the bottom of that page, you'll see my honorable mention. But there's a link in there too. Let's see, is that near the top? Yeah, right at the top. There's a photo gallery, and if you click on that, you will see just image after image after image of the awesomeness that was that show. Um, some really cool stuff, and you know, got to be honest, there was some junk in there too. There was some junk, but you know, it was sort of like, huh, how did that how did that get in here? But you know, it's hard to judge those kinds of things. You know, this is just my personal opinion, right? I mean, somebody else looks at things, and it's like, oh my God, that's the most amazing thing I've ever seen in my life. So, you know, what I call junk probably isn't. But yeah, you know, go through that. I'm pretty inspired, actually. Uh, what there are two things that sort of inspired me about this. And look, I'm going to pull it up on the on I'm going to share my screen, and I'm going to pull it up here. So I'm going to force you guys to look at it. um, but there were two things that actually inspired me about this. The first thing was that, you know, honorable mention is pretty awesome. I am definitely honored to have you know, been awarded that. I'm not interested in winning, or I don't care about that. I'm interested in sharing my art, right? But the other thing that was interesting is that another piece of mine, um, I actually sold two um, two prints of it. So you know, there were people that actually liked it enough to yeah, you know, to want to buy it. So I thought that was very cool too. But I'm just sort of scanning through these, and you can see that there's some really good, awesome stuff here, right? Nothing to scoff at for sure. Now this over here, this was the first place winner in the data art. What do you think about that? That was the first place winner of data art. So I think it's very cool. I think this is, um, uh, it's, whoop, I think this is like the surface of Mars, and they took like, I think they took like a CNC machine and programmed it in such a way as to, you know, carve out the little uh, terrain there. So let's just flip through these. You can sort of see there's just a lot of entries here. Lots of entries. Pretty good crowd. It ran for a few days, um, you know, it's not like thousands and thousands saw saw these, but several hundred, I think, you know, went to this show. I went to it on the last day. Oh, there. Okay, so this is one of mine, and you probably recognize that because this is my little icon on my Discord server. So it's nice to see people actually looking at my art. Isn't that cool? Thumbing through these really fast. Great stuff, though. Great, great, great stuff. I was so glad. I decided not to go to the opening event, mainly because I live like over an hour away, and uh, yeah, it was just a last minute thing where it's like, no, I'm just not gonna go. Just not gonna go. I probably should have, but you know. So there's third place in data art. This was the People's Choice winner. Should I go through all of these? No. So there's mine with a little honorable mention thing that I just showed you, and these are mine as well. I call these orbital snowflakes. So this and this is actually exactly the same data. I just represented it in a different way. I forget what that one oh what that one's called, but yeah, I thought that was pretty interesting. Very cool though. There we go. So you can sort of get an idea of the size of this now. This was the first place winner in data art, but you know, big exhibit held on on the campus of the University of Arizona at the Lunar and Planetary Laboratory main building. Like this, it took up like 2 or 3 floors. So yeah, I am totally into art. I think that art and science are just so related. They're they're practically one and the same. I mean, a lot of the papers that I read, a lot of the plots and a lot of the pictures and whatnot are just awesome. So there's somebody else looking at my thing. This I call magnetic labyrinth, and I think I think I posted a thing on this over on Discord. This is just this uses data from the flux magnetometer aboard the Juno spacecraft that's at Jupiter right now um, to make this. So yeah. It's just kind of interesting. But I think this is Mercury. I shouldn't go through all of this because I've got other things to show. All right, so let me uh, let me switch gears here and um, let's. I posted some stuff from the work that I've been doing trying to characterize my telescope and CCD. So I I just sort of wanted to go through that a little bit. So this is my master flat. So this is a measure of gain. This area here, you could ignore the dark area down here, and you could ignore the white area here. It's just the display, right? But the actual CCD image is this. It's sort of, interestingly enough, it's got like this little white border around it, except for this big black blob. So mainly what you're seeing here is two things. You're seeing the sensitivity uh, of the CCD itself, and that's why you sort of see brighter areas and darker areas like that. But what you're also seeing is anything in the optical path, and that's what all these rings are. These are out of focus pieces of dust, and there's big ones and there's little ones. Let's see, can I? Yeah, I don't think it's much larger, but yeah, it's not much larger. Um, this I know. I was actually looking at the um, CCD array today. This I understand. This dust is somewhere else. I'm not exactly sure where. Now this might look terrible, but actually this is pretty typical. Sometimes it's not quite as dusty as this, but this is a pretty typical flat field because there's dust everywhere. So what this does, as I said, this overall is a measurement of gain, right? So the darkest stuff here, um, uh, and going to the brightest stuff here is plus or minus like 5% or so. So it's very subtle, right? I mean, I've stretched this so you can sort of see it. So, it's exaggerated, but this is the typical flat field. So if you were there when I took this data, I took 4 sets of data. I took 10 images of 1 second, 1 second exposure, 10 2-second exposures, 10 3-second, and 10 4-second. And then I combined all these, I normalized them, which in this case means that I divided each image by the mean value, the average value. In stats, there are uh, there are a number of different ways of representing data, right? You can look at the average, you can look at the maximum, you can look at the median, and you can look at the mode. And all, depending on what the distribution of pixel values it is, though those numbers are typically all different. And in this case, yes, indeed, they are. So yeah, that's actually one of the things that I want to look at. I want to create a different master flat that instead of normalizing to the average value, I want to normalize to the maximum value and see if that changes my results, because I'm getting some uh, interesting but frustrating results. So, all right, let's go back. Here's this next one is my master dark, right? So the the actual images I collected that night were all half-second long exposures. So I took a series of 50 half-second exposures and just averaged them. So I added them up and divided by, well, I added them up, and then each pixel value I divided by 50. And that's what you get. So this is what's called a dark frame, and it's just an offset. It's like a pedestal. It's the electronic noise. It's the thermal noise of the CCD camera. It also shows other things like all these defects, right? There are hot pixels that are, causing these columns to sort of bleed like that, look extra bright. You can sort of see that there are other, bad pixels here too. It's relatively speaking, it's a pretty good CCD, but um, it definitely has its defects. So when I go to reduce my science data, the first thing I do is I take this master dark and I subtract it from all of my data, all of it. And then I'll take my master flat and I will divide this into my data. As I said, this is a measure of gain, and this is just a measure of offset. It's like a pedestal. So I subtract this, and then I divide this. And in this case, I took 200 images of a binary star called STT101AP. And this is just a sort of a random binary star that has obviously two stars, an A component and a B component. A being the brighter and B being the fainter of those two. And I took 200 images. 200 I just sort of arbitrarily chose. I wanted to get a lot of data, but I also didn't want to sit there all night long. So what I did in that case, for some reason, my little cursor thing is not moving. There we go. So what I did in this third image, you'll see here, which is sort of hard to see. What I did is I took all 200 images and I stacked them on top of one another. Now there are two challenges that I have in terms of stacking. The first is that my telescope doesn't track very well. I have no way of guiding extremely well. So I'm relying on just the tracking, which actually that night was better than what I normally see. So I was happy with that. I was actually able to walk away from the telescope several times, come inside, wander around a little bit, go back out, and this binary star was still there. So, but, it does wander around. It does wander around a little bit. The other challenge that I have is because this telescope is an alt-az mount, there's this thing called field rotation. So as the object moves through the sky, it appears to rotate. And so what I have to do is if I want to stack these images up, I have to be able to both shift the images around, move them in X and Y um, to some kind of reference place, and I also have to be able to rotate them. Okay, so what I do is um, these CCD images are 765 pixels wide and 510 pixels high. And so what I've done here is I have created a 1500 by 1500 pixel um, 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 array, and I have placed each of the images into this array, doing the shift and doing the rotation. So that's why you're seeing all this weird um, stuff up here. Because what I want to do, of course, is I want the binary star to exactly stack, right? So I have to shift images and I have to rotate them, and then um, I stack them. And then I can grab a chunk out of this, right? A 765 by 510 chunk out of this, and then um, use that for the analysis to come. But I just wanted to show you that yeah, the tracking isn't all that great, and I've got to take into account rotation. So this is just to show um, um, that process. And another thing that most astronomers do is they do write their own software, and I am no exception to this at all. This is all my own software. It's you know there are two motivations for writing my own software. The first motivation is sort of a control thing, right? I mean, I know exactly what the software is doing because I'm programming it, right? The second thing is that there is software out there to do this kind of stuff, but there's always a learning curve, right? There's always a learning curve trying to understand exactly what it's doing, what parameters it needs, all of that, right? So either way, either way, there's a lot of effort, um, lots and lots of effort, and really no one way is better than the other, um, except in the cases which usually usually are the case that you have some kind of specialized thing that some kind of off the shelf software isn't going to have, right? I don't know if that's any bigger this way or not. No, not really. But anyway, so there's the binary star. There is the A component. There is the B component. And in the next image, actually, I sort of get into that a little bit more. So let's go down here. Dun, dun, dun. Come on. Here we go. Okay, so this is my stacked image, and I'm showing the sort of the noise floor here, and I like to see what's in the muck, right? Because um, as they say, the devil is in the details, and yeah, there's a lot of interesting artifacts um, with this camera that I'm still trying to understand a little bit. Now this is a reversed image, right? So everything black here is actually bright, and everything white, except for the border, is actually uh, faint. Sometimes when you look at, especially images like this where you have stars, um, it's just it, it seems as though our brains are sort of biased towards towards this kind of view as opposed to white on black. So, but this is looking way down in the almost into the noise. You can sort of see that there's a granularity here because I want to look at the actual noise, right? But as you can see, this is a stack, and there's the primary, there's the secondary, and then there's some other little faint stars popping out as well that you can't see in the individual images, but when you add them up, properly stack them, there they are. So yeah, you know, just a few. Not quite sure if this is a star or if this is some kind of an artifact that just um, wasn't removed in the reduction process. This star over here is a little bit extended, which means that my rotation probably isn't perfect. Um, I rotate based on the coordinates of the primary star here. That's sort of what I've used um, as a reference. So the fact that this is sort of stretched this away doesn't surprise me too much. But the surprising things here are these little tails, and I think that has something to do with either the readout or the actual shutter. There is a physical shutter um, on this camera, I believe. Pretty sure. I need to check that out a little bit more. Um, some of this is diffraction. Not quite sure. Not quite sure from what. And then there's this weird thing coming off of this guy. So I'm not quite sure what's going on uh, with all of this, but that's why I like to look down in the muck, right? I like to look down and see what's going on at these really low levels, because um, this definitely is not very bright, right? This thing is not very bright, but it's spread over a large area, and so you know um, that's going to change things a little bit. Now, is it enough to change things so it like completely ruins my data? No, not at all. This is extremely low level, extremely low level. These are too. So yeah, but I've got to understand these a little bit better, um, because yeah, I need to be able to take them into account, and I'm obviously not at this point. So, you know, I I like to let nature sort of guide me and tell me things, and yeah, it definitely is. But that's not bad. You know, I think I'm pretty sure these were still a little bit out of focus. A little bit out of focus. Focus is really hard. What I want to do is I I'm either going to buy or I'm going to make a I forget what they're called, but they're a it's a mask that goes onto the front of the telescope. And if you point your scope at a bright star, this mask will create a particular pattern. And depending on your focus, the pattern will change. So at, at perfect focus, you'll see, you know, um, a particular pattern. And that's what I have to do in this case. The way that I'm focusing now is that I sort of run the camera really fast, and I look at the maximum value. So as I defocus, um, this light will get, you know, spread out, and the maximum value will drop, right? So I can go in and out of focus and see that happening. And when I get to the the highest maximum value, I know that I'm pretty close to focus. But I think I was still out here. I think I was still out. So yeah, you know, that's something that I have to work on for sure. This isn't bad. It's not bad. Not bad. Um, let's see. So let's go on. So then I started the I've got one more thing to show you here. I went over to Gaia and grabbed the um, uh, sort of the field where this binary star is. And as you can see, here's the primary, here's the secondary. Here's these sort of 2 or 3 stars here, and there's this star way over here. So you sort of have to look at this. You could maybe have to tilt your head a little bit in order to line things up. But as you can see, let's see, can I get both of these? I think I can get both of these in the same, oh, get these both in the same field. Come on. No, we don't want to delete. Up here. I get these in the same field, almost. So you can see, here's the binary. So here it is, right? Here's these, at least these 2 here. And then on the same side as these 2 is this guy way over here, and that's him. That's him. So yeah, you know, I'm seeing the right things, no doubt about it at all. So then comes the analysis. Then comes the analysis, and that's what these plots are. So this is a plot showing the brightness of the primary star as I measured it per image, right? So this isn't the brightness of the stack. I took 200 images, right? So the x-axis here is going from 0 to 200. And then this is just the brightness. You can see here that I've plotted this on a logarithmic scale, right? So here's 1,000, here's 2,000, 3,000, 4,000, 5,000. Here's 10,000, 11, 12, 13, 14, 15, 16. No, I'm sorry. 10,000, 20,000, 30,000, 40, 50, 60, all the way to 100. Here's a million. Here's 10 million. So this is just, I just measured. What I do is I, let's see, we can go back to here. For each individual, oh man, why are you doing this? Stupid. So for each individual image, right, what I do is I draw a little circle around here, just on the edge, just outside of this dark thing. And then every single thing inside of that circle, every pixel, I look at the data value and I add it up. I just add up all the pixel values inside of here and inside of here. Okay. Now, I also have to take into account the fact that I'm looking at sky. This is all sky back here, and the sky has a brightness as well. So that's a lot like the dark. It's another pedestal. So I also, what I do is, so I've defined a little circle around the star. What I then do is I create a little annulus, like a little ring around the star. And I measure the pixel values there as well. And that's my sky, right? So then I subtract the sky from the star and I get the actual star pixel values as if there wasn't any sky, right? And I do that for the A component and the B component. So that's what, whoops, that's what this plot is. This is just the star values. Actually, um, star minus sky for the primary star, the bright one, and the secondary star, the fainter one, right? And grab my notes here. So the primary star up there, the average value here was 908,607, plus or minus about 33,000, or about 3%. So I've got a 3%, actually 3.7% error here in my measurement of this bright star. 3.7% is not bad. It's not really, 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 really good, but it's not bad. Anything less than 5 isn't bad. Ideally, and what I'm aiming for is about 1%. So I'm going to have to work on this a little bit. Work on my well, I don't know if I can get 1% or not. This is part of the project, is to characterize this system, see how good I can get. And usually, the brighter the target, the less noisy it is. And you can sort of tell that this is the secondary star, much fainter, and noisier, right? So that has an average value of 6,996, plus or minus 460, or plus or minus about 6.6%. So, but you can see that, this is essentially time, right? So you can see that there was a period of time where actually it was really, really, really nice. Right in here, not a lot of wiggling around at all. So pretty impressive right in that area. Probably what I'm going to do is I'm going to extract just those images, and then I'll do a stack and make some measurements there as well. But this I can definitely say in both cases is pushing 1% error. So that's not bad. That's not bad at all. But overall, I'm really, really pleased. These are really flat, right? Really, really flat. They don't, go up and then down and up and down or anything like that. They're very, very flat. So they're very consistent, right? My um, precision in terms of consistency is pretty good, pretty good. So I'm pretty happy with that. Pretty happy. So then what I can do is I can take the brightness measurements that Gaia took, right? So Gaia measured the brightness of this star and this star, right? And I can calculate the difference in magnitude, difference in brightness between those two stars as measured by Gaia, okay? And I can say that the magnitude of the primary star is magnitude 4.548, and the magnitude of the secondary star is 9.442. Okay, so there's a difference there of 4.89 magnitudes. So 4.89, every magnitude is a factor of 2.5. So we can go 2.5 and then exponent that 4.89, and we get a factor of about 88.3. So the primary star is 88.3 times brighter than the secondary star. Okay, 4.89 stellar magnitudes. Okay, that's what Gaia says. Okay, now I can do exactly the same thing, right? I can take either this data, right? Either this data or my stack, right? Of all, well, almost all 200 images. And I can also measure the difference in magnitude between those two stars because I've got a measurement of the flux, right? And what I get in terms of differences is this last plot. So these are my measurements of the differences between each of those stars per image, right? Per image. And as you can see, I'm getting a difference of about 5.28 magnitudes. If you sort of look at the average here, 5.28. Okay. Now this red line here is what Gaia says that the difference is. And this is the difference that I measured. Now, I can say that my precision is actually pretty good. This is plus or minus 0.08 magnitudes. So my precision is really, really good. I mean, it's noisy, but I'm around like 1.5% in terms of the difference in magnitudes. So I'm pretty precise here, but as you can see, my accuracy is about 0.4 of a magnitude off. So it's as if I'm, playing darts, right? And I can throw 200 darts, right? Throw 200 darts at this dartboard, and instead of instead of hitting the target, right, hitting the bullseye over and over and over and over and over again, almost exactly in the same place, I'm hitting off to the side over and over and over and over and over again. So my precision is really, really good, but my accuracy is off. But the interesting thing is that it's consistently off, right? All these are less than that by, pretty much the same thing all the time. So the dilemma that I have, and actually this is pretty consistent with the other data that I've looked at. I've been seeing this, 4/10 of a magnitude difference between what Gaia says and what I say. So the fact that this is so consistent, see, I mean, if I had, differences here and then up here and then here, all over the place here, then I would sort of be like, okay, yeah, my precision isn't all that great, might be accurate, but your precision is all over the place, right? But the fact that I'm pretty consistently about 4/10 of a magnitude off, that's telling me that there is something systematic that I'm just not quite I'm not quite there yet. But I think my measurement is probably okay, but I'm not taking something into account. So there we go. There we go. I did photometry on the stacked image as well. So these are the individual images. I can also do photometry on just the single stacked image, right? I can measure the difference in brightness here, and I'm getting pretty much the same thing. I got I wrote it down here. I got a difference of where is it? About 5.25 magnitudes or so. So as opposed to 5.28. So yeah, pretty much the same. So yeah, there's something going on that I'm not understanding quite yet. There's some kind of translation that needs to take place between my data and the Gaia data. Not quite sure yet. But it's pretty cool. I'm actually relatively pleased with how that came out. I'm gonna stop sharing my screen now. Cheers. Pretty happy with how that came out. As I said, I don't know why there's a discrepancy there, but I'm consistently off. So that tells me that there's some kind of a systematic thing that I'm not taking into account yet, and I will figure it out. And as I also said, when I look at my previous data, I was seeing pretty much exactly the same thing. I was seeing that I was off. I was low by about 4/10 of a magnitude. So don't know what's going on there. Precision, I'm happy. With 80 millimagnitudes. That's a good number. I'm happy with that. I'm pretty much happy with anything less than about 1/10 of a magnitude, 100 millimagnitudes. So that's where I want my accuracy um, to be too. The fact that I'm seeing precision that um, at that level is very, very, very awesome. So yeah, overall pretty pleased. Kind of frustrated with why those aren't more the same, but I will figure that out. I don't know exactly where that is yet. I was hoping the reason why I went to binary stars was because to I wanted to get some brighter stars, right? I mean, um, the stars that I've been looking at prior to this were all part of clusters, and were pretty faint. You know, 8th, 9th, 10th, 11th, 13th magnitude, 14th magnitude. Not a lot of signal, right? Not a lot of signal, even in the stack. Just not a lot of signal. So I was like, okay, well maybe the accuracy isn't there because I don't have enough signal, right? So it's like, okay, look at um, some brighter stars, but because I'm looking at differences, um, I have to guarantee that I have at least 2 stars, right? So hey, look at binary stars. Look at some bright binary stars. And so that is what I've done in this case. And um, so what I was hoping, it's like, okay, more signal, then I've got, you know, a little bit more, you know, meat to grab onto in order to make the measurement. And when I did that, I'm coming up with pretty much exactly the same thing as I'm seeing with previous data. So what that tells me, right, is that it has nothing to do with the signal, with how bright these targets are. It's something else. It's something else. So it's cool, right? I mean, you know, this kind of work is oftentimes like a process of elimination. It's like, okay, here's my result. I'm not happy with that result. I'm seeing a systematic problem, right? So there's got to be a cause. There's got to be a cause. So I'm thinking about, okay, it's like, what would cause this? Um, and uh, so I make these lists, right? It's almost like a mental list, but it's like, okay, it could be this, it could be this, it could be this, you know, this is this. So I can now scratch off the list. Uh, brightness, signal, it has nothing to do with um, um, signal. The fact that I'm getting, you know, really good precision um, means that it has nothing to do with signal at at all. If there was, you know, this huge scatter and all that, then okay, yeah, maybe, but I'm not seeing it. So it has nothing to do with with that. Um, could be focus, could be focus. It could be tracking, probably not tracking. Could be tracking. Um, could be how I'm reducing the data. As I said, my master flat, um, I'm normalizing by the average value. Maybe I should normalize by the maximum value and see if that makes any kind of difference. The you know the reason why um, I'm looking at the differences in brightnesses between stars is because it eliminates lots of systematic problems. Atmospheric extinction is gone. Um, um, uh, yeah, you know, I'm trying to think of other systematic things. Um, stuff like, you know, not very good reduction calibration of data, um, looking at differences, those kinds of things should be eliminated, really. Um, so yeah, don't know. This wow, it's already 3:10 UTC. Where does the time go? It must be it must be the fact that I'm having so much fun. So can't help it. Hey there, Andy. Nice to see you. You're coming in right at the end, but nice to see you. I was just you'll have to rewatch this. I was talking about um, the data that I collected with this telescope a couple of nights ago, um, trying to understand why I'm seeing differences between what I'm measuring and what Gaia um, says things should be. So make sure to rewatch that if you're interested. But yeah, it's already 3:11 UTC. It's unbelievable. As I said, I must be having way too much fun because that was a very, very, very fast hour. And I want to keep these, to about an hour or so. I guess we talked about art as well in sort of the first third or first half or so of the live stream tonight. So yeah, that went a little bit longer than expected, but I don't mind those kinds of um, um, tangents because we're talking astronomy, and it doesn't really matter what we talk about as long as we're talking about astronomy. So very cool. All right. Well, I'm I'm going to get out of here. It seems like it went really, really, really fast tonight. I mean, I didn't even, I just got a couple of sips of this hydrogen hydroxide tonight. What is going on? Glad you like the shows, Bobby. You come on in anytime you want. Uh, yeah, you know, as I said, I am gathering a circle of friends in sort of a virtual lounge area, uh, and we talk astronomy for about an hour, usually over an hour. But you know, I definitely respect your time. I know that you've got uh, um, other channels to watch, other live streams to monitor, and I'm glad that you choose to plant yourself here for a short time, talk astronomy for a while, and watch the struggles of at least one of the pros. So yeah, it's tedious, painful work, and a lot of hair pulling does occur when you're um, when you've got data to look at. So yeah, painful, painful, painful. Yep. Hit the like if you like. Hit the don't like if you don't like. That's okay. That's all right. I'm always trying to improve. I think I'm trying to make this live stream better every single day, and I'm getting a lot of practice. And my success will bear itself out in time because yeah, I think just getting better um, better and better is the goal, is sort of a secondary goal. The number one goal for this and for everything is to have fun. Definitely, definitely, definitely have fun, enjoy. Um, if I, communicate things, cool. If I um, um, educate um, a little bit, that's cool too. But I'm here to share a passion and just give, and give and give, and yeah, receive as well. This I like this back and forth stuff. So yeah, very very cool. Um, Twitch edu, yeah. Well, I think um, Uncle Bill, I think the educational part of Twitch is definitely gaining momentum. I hope to be on Twitch at some point. I just need to have a better uh, setup here, and then I definitely want to get on to Twitch. Excuse me, as well. All right. For now, though, it's going to be YouTube. It's going to be Google Hangouts. I think it's awesome, regardless of what the um, format is. I think it's very, very cool. But for now, I'm going to get out of here. Peace. Cheers. Hold on to your hats because we are moving fast. We're moving fast. Every single day, we move 20 million kilometers in some direction, right? We are moving fast. We're moving really, really fast. We don't really even know to what extent we are moving, but at least in the ways that we know and understand, we're moving. We're moving a lot. So hold on to your hats. Don't get dizzy. It's all right. It's a smooth ride. You're used to it. We will gather again tomorrow, same time, same place, 2 hours UTC. Peace, cheers, and I'll see you on the spin. Bye.